Hi, welcome back. In this lecture, I want to go through some practical aspects of the implementation of the FEM. In particular, I would like to study the problem that we already seen when solving the Poisson equation in the coaxial transmission line problem in the second module of this course using the finite difference. So we're going to see how to use the FEM to solve the very same problem. In the previous lecture, we look at a practical aspects about FEM, that is meshing. So we are going to start again to look at how we can do meshing, how we can read mesh information in MATLAB. What I want to describe are basically the typical data structure using for meshing, and then I'm going to spend some time also on how to assemble the global matrix. And we're going to use the nodal basis function as subtriangles areas, and also we are going to look at a single component of a matrix, the so-called element matrix. We are going to study MATLAB code for solving the coaxial transmission line problem, that is solving the Poisson equation in the problem we saw in the second assignment. So how do we store information about mesh? In the previous lecture, we described the basic technique. In assignment 3, exercise 2, we will use a preform mesh stored in a file called unimesh0.mat. So the first step will be to load unimesh0.mat in MATLAB. As soon as we load this file, we will see that there are basically two data structures, that is L to nodes and nodes to X and Y. The example that we're going to look is the very same that we saw in the previous lecture. So we have a global indexing for the elements from 1 to 4. So we have 4 triangular elements, and then we have global indices for the nodes from 1 to 6. So the first data structure that we are looking at is L2 node, that is the element to node matrix. That is nothing else than the connectivity matrix that we discussed in the previous lecture. By using L2 node, we map the elements to the global nodes that are the vertices of each triangle in another matrix L2 node. So this is what we call the connectivity matrix in the previous lecture. So on the columns we have the numbers of the elements, and then we have the number of the indices of the nodes that correspond to that particular element. So the important things that when we number is that we choose the node in counterclockwise way. So for instance, let's take element 2, that is this one. There will be element 4, 2, and 5. So this column is going to be 4, 2, and 5. However, as we saw when we assembly a matrix for defining element methods, we also need the information of the coordinates of the nodes. We are going to use the coordinates of our nodes to build the basics function that is at the core of the FEM. For this case, we are going to use another data structure called node to XY, that is going to map the global node number to its coordinate xy in 2D or xyz in 3D. So let's look at an example here. We have 6 nodes, so we will have 6 columns, and for each columns we will have the coordinate xy since we are in 2D. So let's take for instance the node 4. The first value will be 0.6, that is the x coordinate, and y value, the y coordinate is going to be 0.4. So this is the column here. We map each node to the x and the y coordinate using these node to xy data structure. So the example that we have here, so we load the mesh information for the mesh representing the left part of the slides, and we see that we are having two matrices. One is node to xy and L2 node. So each column is in this case is the element to the node, and in this case is from the node index to the coordinate. So let's look at the the problem that we solve in the second assignment when we calculated the potential in a coaxial cable transmission line. So as far as you probably remember, so there is a outside box, and then there is an inner part, and then we put boundary condition on the inner boundary, outer boundary. That is a difference of potential. So in this lecture, and also for your third assignment, you're going to try to solve the very same problem but using the FEM method. The first step to solve this problem in the FEM method is to load a matrix with all the elements. So this is 2D problem. I'm going to use triangular meshes. For this problem, we calculated the mesh for you, and we provide in a mesh called unimesh.0. So the first step is to do load unimesh0.m, and once you load this, you will see different data structures. So one is going to be the mapping from the element index to the node indices, and the second one is going to be from the node indices to the x and y coordinate. So if you do this in MATLAB, you will see that you will have two matrices. The first one is 3 by 252, and the second one is 2 by 156. So the question here is what is the number of nodes that we have? Well, we can easily calculate the number of nodes by taking these matrices here. So in this case, node to x, y, and then take the second dimension. So in this case, it will be 156. What is the number of elements? So in this case, we can use these other data structures, all to node, and get the size of the second dimension. So in this case, it will be 252. So just to summarize, this mesh is going to have 252 elements and 156 nodes. An important part of the meshing is also to provide which nodes are the one at the boundary. So in this case, we're going to have two kinds of boundary condition. One on the internal part of our rectangle, and then on the other outer part. Since these are going to be Dirichlet boundary condition, we need to know what are the node indices of these boundaries, so we can fix the values of these nodes to a given potential. So what we're going to have in our mesh is also information about which nodes are the boundaries. So we have two additional data structure to characterize the boundaries. The first one is no extern, that is the global node number or index for the external BC, so the one on the external boundary condition. And also we are going to provide what is the global node index for the internal BC using no int. So you see this additional information about the indices of the nodes for the boundary condition. So by these data structures, basically loading the information from our unimesh 0, we can also plot using this very simple script in MATLAB. You can see also detailed information how to plot the grid. So if you do this, then we obtain this grid here. So this is very much the same problem that we solve for assignment 2. We see that we are using triangle meshes. For one important difference is that for our second assignment, we only use 1/4 of the domain, and then we applied normal boundary condition on this axis here and this axis here. In this case here, we provide we do a meshing of all the domain, so we don't use this condition, this boundary condition, and reduce the computation using the symmetry. So that's the first step. The very first practical aspect is basically load the mesh, understanding how the mesh is formed, how many elements and how many nodes are present. The second step that I want to spend with you some time is actually how to build the assembly matrix A that will constitute the matrix that we are going to use to solve the linear system in the FEM. So if you look at the governing equation we started, for instance, for the 1D problem, we use the Helmholtz problem. So there's alpha multiplied by second order of our derivative and plus beta multiplied by the first order of our derivative, and then we have gamma multiplying the function in itself. So that is the general Helmholtz problem. Here what we're going to do is to solve the same problem but in 2D. So an important point that we derived during that formulation is that we can form an assembly matrix having a different term. In this case, phi are going to be our interpolation function. Our interpolation function or basis function. So the elements I, j of the system matrix are computed by evaluating the integral over the domain S. That is all our domain between the inner and the outer conductor of our problem. In the assembly procedure, that is to form this matrix A, we break up this integral into integrals over each element E and sum the contribution from all elements, where n is the total number of elements. So this is the very first step, and the second step is to eliminate this term here, because the problem that we're going to solve is the Poisson equation, that is only second order differential equation, so there is no contribution from first order, no contribution from the function itself. So this term here and here, they go away. And then we have this term over all the domain. At this point, we can recognize that we are going to split our domain in many elements. So we can split this integral by calculating a smaller integral on each one for the element, and then we sum it up, all the contribution from 1 to all the elements. So the problem is the following. So what we are going to do is to calculate that integral for one simple element, that is a triangular element, and then we are going to sum it up, all the contribution from all the element. So let's calculate the integral for just one element. As soon as we know how to calculate this integral for one element, then we can sum it up, all the contribution for all element to calculate the big assembly matrix. So in this case, we use the local numbering of the nodes for the element E, as shown in this figure. So we have 1, 2, and 3. That are this local numbering of our element, and the node coordinates of the node as R1, R2, and R3. So this is going to be R1, R2, and R3. So these are basically vector. The element matrix, that is a tensor. So since there are 3 basic functions in each element, each one for each node of the elements. Remember that the interpolation function or basis function are those functions that are equal to 1 at that particular node, and then have the linear behavior next, and y in the adjacent node, and then 0 all outside these nodes. So we can keep the information about these 3 basic functions using a 3x3 matrix that we call element matrix. So we are going to call Aij of E. So this is element matrix that take into account basically the contribution of the basic function in one element. So for your assignment, you're going to use a function that is called CMPL matrix, compute element matrix, that is going to take as argument the coordinate of the points, and then provide these 3x3 matrices. right? So in this case, we provide as an input the coordinate of the 3 points, and then the y coordinate of the 3 points. So we give as an input the coordinate of the nodes of the element, and we get as a result the 3 by 3 matrix. How this element matrix is calculated? So it's calculated analytically by using geometrical consideration. So we provide a set additional slide, or also you can consult the textbook to deduce this formula here. So this is a formula that is given or can be derived, and is going to provide for us the total area of the element, and then by the total area of the element we can calculate this quantity that is the gradient of the vectors, and still we can use geometrical consideration to calculate this. So once we know how to calculate this gradient here, we can calculate this term here. So just to summarize, this is a function that take as argument the coordinates x and y of the 3 nodes of the element, and it gives as a result the element matrix that is a 3 by 3 matrix that we're going to use to assemble the global matrix. So this is the contribution for each element. So the calculation you see in this function are basically using the equation that are derived from geometrical consideration. I strongly suggest you either to look at the additional slides in this lecture, or to look at the textbook that is going through the calculation of this specific term here. What I'm pointing out here is basically the different part of the codes that are using this equation. One part of our work is actually to define the boundary condition. In this case, we know what are the boundary condition. We know that we are going to use Dirichlet boundary condition in the inner and outer boundary condition, imposing a difference in the potential of 1 volt. So this is extremely important in FEM, because what we can do is we eliminate the extra equation corresponding to the node at the boundary, and we fix those values to a given value. So the right hand side, the vector b that we're going to use when we solve the linear system, is constructed following the very same assembly procedure we use in 1D. And also we are going to follow the same procedure we saw in the previous slide, that is summing up all the contribution coming from each element. In this case will be bi of E, where E is the element. So often A, E, and BE are evaluated numerically rather than analytically. So in this case, we use some geometrical consideration to calculate. So now we have one row in A and B for every node in the mesh, including those where the solution is known from the Dirichlet boundary condition, where we can just fix those values. So this is not exactly what we want, since the test function must be 0 along this boundary condition. So we want to exclude from our linear system those nodes that are boundary conditions. So we don't want to have extra equation for those. We just want to fix the nodes value to the Dirichlet boundary condition. So the process that we're going to do is to remove the rows in A and B that are corresponding to the nodes where the solution is known, right? That is where we have the boundaries. And for doing that, we're going to use those two data structures, that is no X and no int. So let's look at all the program all together to solve the Poisson problem using the FEM. The first step is to load the mesh. So we load the mesh, and then we calculate the number of elements and the number of nodes. We do some scaling to go from meters to centimeters. So we multiply the coordinate of each node to 10 to the minus 2. So we divide by 100 to get centimeters. And then we initialize the assemble matrix and the source term with 0. The most important part is actually the assembly of the matrix A that we are going to solve using a linear system solver. So the basic technique here is that we're going through each element, and for each element we are going to calculate the element matrix, and then we're going to add the element matrix to the global matrix A. So here is actually the following. We first get the node indices, and then we calculate the coordinates of the nodes by using the two data structure. We use a compute element matrix, that is 3 by 3 matrix, calling the function we saw before, and we obtain this 3 by 3 AL. After we obtain AL, we just sum it up in the right place. We add the contribution to the global matrix. If we put all together, so we go through all the elements in our matrix, we can visualize the sparsity of our assembly matrix A. We can use a SPI parenthesis A that is going to give the non-zero value. So as you can see, the matrix is quite sparse, but there are some interesting pattern. An interesting point here is to notice that the matrix is symmetric, right? For the problem is self-adjoint and method is Galerkin. So we expect to have a symmetric system. One important point, as I told you before, is to eliminate those nodes that give equations at the boundaries. So the way to do that is to use information that we have from the nodes, from internal and external boundary, and eliminate those from our equation. So that's the next step that we're going to do. As soon as we've done that, so we have all the equation for the inner boundaries and we fix the values for the outer boundary, we can calculate the values of our unknowns by simply calculating the linear system solution by using a / command in MATLAB. And then the final step is actually to calculate the capacitance from the value of the potential. Actually calculate the capacitance, calculate a W, that is so from energetic consideration. So it's slightly different from how we did in the assignment 2. So this is the way to calculate here. So we calculate from energetic consideration. But the real problem in this is how to calculate the potential. But then, from the potential, we can calculate the capacitance. This is the last slides of my lecture. I also provide some additional slides to recover some of the formula that we have been using to calculate the element matrix. All these are based on geometrical configuration to calculate those integrals. The textbook also details the steps to calculate this expression. So this is the last slides. In the next slides, we start looking at how to use FEM in the case of a vector quantities, not just a scalar. Talk to you soon.